Hey folks, Sonic fan here, hacking and repairing an electric screwdriver. I posted a couple videos on these and I'm a big fan of them, so they're worth my time to repair. This one has an interesting failure that I think I have successfully found a workaround for a partially failed chip. The way this works is actually really fascinating. It uses just a lithium-ion battery controller, which is this chip right here, the S8261. Did a lot of digging to find out what that was. That's a lithium-ion charge and discharge controller, and then it controls this very large FET as current regulation and voltage regulation. Of course, it has for the battery. So it's essentially just a lithium-ion protection board, a fancy lithium-ion protection board, and then the switch here activates the output from the drain from the N channel FET here, and reverses the polarity as well. It does that mechanically. So when you go forward or reverse, you have to reverse the polarity of the two pins on the motor there. Now, this is not the FET that it came with. I replaced this. It comes with an A0 or A206. It's a trench MOSFET. Seems to have really nice specs, actually. Really powerful. This one's a less powerful with lower specs. The RDS on is a little bit, quite a bit higher, actually, 10 times higher. So it's going to get a little bit hotter. It's not as efficient. Hopefully I'll eventually get the actual one that it came with. And then a couple interesting things. So the schematic for this chip shows that you're supposed to have a minimum of 300 ohms between the power rail to the chip, whereas stock, this actually has, there's two 4.7 ohm resistors in here parallel, and then a 100 ohm resistor. So it's actually not meeting the spec of the data sheet, which I think is interesting. I went ahead and added a 470. We'll see what that does. But where this failed is there's a pin called VM, which I believe is pin 2. And how this works is pin 2, it goes across a sense resistor to the output and measures the load from that sense resistor. This is a 680 ohm resistor originally. And there's a pull-up resistor in the chip. And that pull-up resistor in combination with the sense resistor lets it know if there's an overcurrent status. Well, in my case, I believe the pull-up resistor internally for VM is actually blown. This happens sometimes. You get parts of a chip blown internally. And I was lucky enough that if I disconnected the sense resistor completely, it actually turned on fine. But then, of course, you don't have any load protection or overcurrent protection. So I've come up with a little ingenious hack. I think it's ingenious, but I'll let you be the judge, I guess. And this is kind of a cool way to hack a sense resistor with a broken IC. I will replace that chip eventually, but it'll take a month to get one in the mail, and I'd like to use this in the meantime. Of course, I could just bypass it, but then you get some dangerous situations where you might blow up that battery, and that would be bad. So I wanted the overcurrent protection, and I wanted to do the best I could with what was in here. So I came up with a little trick. First of all, it does output 5 volts with or without that sense resistor. It's just the minute you hit this switch, it thinks it's in an overcurrent state. So what I did was I wired up a potentiometer here. You can see this is a trim potentiometer where the sense resistor was. And the sense resistor, which was 680 ohms, I knew that an open circuit let it run. So I just slowly dialed this up to the point where it would run. So what I found, that was about 8 kilo ohms. It seems to be happy with that. And then I hooked up this voltmeter to the output of the trench and channel FET. And that way I know when it's powered on. And as you can see, it actually shuts off for a second. My guess is there's a voltage drop. It might even drop below the 3 volts when I do that. Either that or there's no, I guess it would have to be a voltage drop. Anyway, so you can see it's doing something though. And here's the cool part, is I got this 2.2 ohm resistors, a 5 watt big bulky resistor. These are great for measuring output loads. And you'll notice if I put this across, that's like an extra 2 amps or so that it's going to be funneling into this in addition to the motor current. And when I have this connected and I hit the switch, whoops, it's hard to do this with one hand. You'll see it shuts off. And it completely shuts off. What's interesting is it's actually still reading the output of this voltmeter. So if I disconnect that voltmeter, which I will do right now, even though this is kind of dodgy to do on camera, and then I reconnect it, ta-da! So that's how I know that the overcurrent protection is actually working. It's pretty cool. And in fact, if you wanted to, you could leave this this potentiometer. It's a rheostat, essentially. It's set up as a rheostat. In the unit, you could even poke a hole and make it accessible, and you could adjust the current protection based on that, which is kind of cool because that means like this has an upgraded battery from what it originally came with. I'm sure it can output way more current than the original battery, and however, you might want to be careful because whatever the motor is rated at, you don't want to burn out the motor. Anyway, I just wanted to get this. This is kind of a hacky way to do it. If I was being more professional, I'd have all kinds of ways to measure torque and stuff like that. Right now, I'm just kind of checking with different screws or holding my hand on the drill while I press the button, and that gives it that extra load. And so you can see if it's well, you don't want it to struggle. You want it to shut off before anything happens. And what's cool is I have it now where I can really grab onto this, hit the button, and it will continue to turn. But with this resistor, it doesn't. So that lets me know that, it'll be good for unscrewing things. But if there's a problem, like, that causes an extra surge of current into the motor, it will shut off and it will work correctly. Pretty cool stuff. Hacking is fun, kids. By the way, also these resistors here, I repaired another one of these I had, and it had these 4 parallel 10 ohm resistors as well as this P-channel FET, and they had all blown up, so I had to pull it from this one. This P-channel FET you can also pull from the output here. I pulled from the output, which is pretty cool, because that's actually just used to drive the white LED here and switch that on. And then you have two feedback diodes for the motor there, and not much else going on. It uses this PNP. It's a PNP in combination, I think, with this guy as well, little NPN, and the diode. And I think these are sense resistors and this diode as well to charge the battery. It's a very crude battery charger, like not a proper battery charger by any means. And I had to add a fuse because my other one almost caught fire when I put a different charger in by accident. So it's a very crude charging mechanism, but this works really well, and I've used it for years now. And I think it's really cool that the hackers that made this, some really smart engineering, used this lithium-ion protection chip to sort of exploit that as a current-protected motor driver. Pretty cool stuff. Doing a lot with very, very little. I think this whole thing on retail costs about $20. So it's kind of impressive, especially because this is a nice motor. All things considered, it's got a lot. I took that apart. It's got a lot of gears and different things going on in there. Pretty cool, man. Modern electronics. Pretty fascinating. Anyway, go out and buy yourselves a nice electric screwdriver. You can't buy this one anymore, which is why I'm repairing it. But you can get these for like $30-40, and they are great. Can't recommend them enough. Hope you had fun and learned something here. This is Sega Sonic Fan, signing out.